Good afternoon everyone. I am Purnima. My topic is Inception of jump resonance in single phase transformers. Jump resonance is a special case of ferroresonance that occurs between a nonlinear inductance and capacitance in a low loss electric circuit when powered by a voltage source. In power system, the nonlinear inductance is available in power and voltage transformers. Capacitance is available between the cables or overhead conductors as shunt capacitors or stray capacitors, etc. The low loss system is realized in terms of low resistive systems or instrument transformers. The inception of ferroresonance may initiate oscillations which may have catastrophic failures in electric power systems. The differences between linear and the ferroresonance are highlighted here. The nonlinear resonance is possible over a wide range of capacitance value, whereas single capacitance in linear case. The frequency of voltage and current waveforms will be different with respect to the applied voltage source, whereas they will be similar in linear case. The nonlinear resonance has several stable steady state values with which depends upon initial charge and flux values, whereas there is single stable steady state in linear resonance. Jump phenomena will occur when the circuit moves from one stable state to another as a result of change in the circuit values. The inception of ferroresonance can be illustrated using Rodenbach's graphical method. Rodenbach's approach says that the intersection of the voltage across the inductance and voltage across the capacitance curve will give the information about the resonance. Here the red curve is the transformer voltage, that is voltage across the primary winding, and the C1, C2, C3, C4 are indicates the voltage across different capacitance values. If the intersection occurs in the linear region of third quadrant, so this is linear region of third quadrant, if the capacitance is chosen less than C1, there are no chances of over voltage. If the intersection occurs in the saturation region of third quadrant, if the capacitance is chosen between C2 and C3 values, yes, there are chances of ferroresonance inception with over voltage more than 1.2 per unit. If the intersection occurs in the saturation region of third quadrant as well as in the linear and saturation region of first quadrant, that is, if you choose this capacitance between C3 and C4 values, again there are chances of ferroresonance that may induce more than 1.2 per unit over voltage or over current. If the intersection occurs in the linear region of the first quadrant, there are no over voltages at all. There are four modes of ferroresonance: fundamental, subharmonic, quasi-periodic and chaotic. Here fundamental and subharmonic are assumed to be periodic modes, whereas quasi-periodic and chaotic are not aperiodic modes. So ferroresonance is a non-linear complex phenomena having several steady state values which are highly sensitive to system parameters and initial conditions. Any change in the circuit conditions will cause sudden jump such that it initiates any one of the ferroresonance modes. The listed out configurations of ferroresonance are reported in literature. So it is concluded the ferroresonance is initiated after any switching event like load rejection, fault clearing or loss of system grounding. This figure shows the damage due to ferroresonance. The ferroresonance is accompanied with low frequency oscillations which triggers initial early saturation. The high current density due to saturation of the transformer creates overheating and overpressure such that the reactive energy of the circuit is converted to heat and hence the voltage transformer will burn. The ferroresonance circuits are analytically explained using bifurcation diagram, Poincare map, phase plane method, STFT, CWT, soft computing algorithms and PID controllers. How to understand the ferroresonance has occurred? With the help of rattling noise in the transformer or overheating in the cores and transformers, long-term overvoltages and overcurrents, distortions in the waveform, displacement of neutral point, overheating even at no load, thermal failures. How the ferroresonance is being prevented now? If the voltage transformer has a delta connected primary, if the system has grounding conditions, proper grounding conditions, if the voltage transformer is designed such that its saturation point is at least twice the system voltage, by introducing load resistances, by simultaneously closing and opening of the fuses. So here this figure shows there are 3 phases in which only one phase fuse is normal, whereas the 2 phases are not abnormal. Once ferroresonance is incepted, the mitigation circuit being used are a resistor, a combination of resistor and a non-linear inductance, and metal oxide arresters are being implemented to suppress the ferroresonance oscillations. Superconducting fault current limiters, MEM resistors, thyristor based circuits are proposed to be mitigation circuit to suppress the ferroresonance mode. This is my preliminary work which I am presenting now of my research work. My research is about mitigation of ferroresonance using MEM resistor emulators. So you can refer my publications to understand my research work. This is the first time I have realized ferroresonance in my lab transformer. A transformer rated at 2 kVA 220 volt bar 160 volt is chosen and its parameters are obtained using normal OCAC test. So this is the ferroresonance test setup. Here the transformer is supplied in steps of 10 volt through the series capacitor. The value of series capacitance is identified using Rudenberg graphical method. The ferroresonance inception is checked by applying the voltage in steps from 0 volt to 220 volt and again reversing the supply, like reducing the supply from 220 volt to 0 volt. Before being experimented, a Simulink model of the chosen transformer with a capacitance of 5.5 microfarad is modeled using Simulink. The model developed 2.6. The model gives 2.6 per unit overvoltage in the primary and secondary winding as well as current. It also accompanied with the harmonic components, third order and fifth order harmonics, and it shows the THD values also. Here the third order harmonic is predominant. So while supplying the transformer in steps of 10 volt, the capacitance of 5, 8, 10, 12.5 and 20 microfarad are used initially. Among these, only 12.5 and 20 microfarad induces ferroresonance. Before connecting this capacitor, I got normal values as shown in this figure. Out of this, only 12.5 and 20 microfarad capacitance induces ferroresonance. Difference between the Rudenberg value and the experimental value shows the Rudenberg doesn't taken into account of core loss and harmonic components. With the increase in the capacitance value, the supply voltage at which ferroresonance incepts is also increases. While conducting the ferroresonance, the voltages, currents and the harmonics are recorded using Fluke 434 series 2 harmonic analyzer. Here, when the supply voltage is increased from 0 volt towards 220 volt, when the supply voltage is around 150 volt, there occurs a jump phenomena. The primary voltage is jumped from 200 volt to 345 volt, whereas the secondary voltage has jumped from 152 volt to 280 volt. The primary current has jumped from 0.9 amperes to 3.6 amperes. Similarly, power loss as well as harmonic components also experience a jump up. While moving towards 0 volt, again jump down phenomena is experienced. That is, the primary voltage is reduced from 325 volt to 50 volt and secondary voltage is reduced from 256 volt to 120 volt. Similarly, other parameters. Apart from these jump up and jump down curves, there are the curves which indicates with the mitigation technique there is no jump up or jump down phenomena while moving towards 200 volt or while reducing towards 0 volt. As per IEEE standards, a 10% resistive load can be used to mitigate the ferroresonance. So, for the capacity of 2 kVA transformer, 10% resistive load is calculated as 130 ohm and it is connected in the secondary winding of the transformer. While supplying and reducing the voltage, the jump up and jump down phenomena has not occurred. This proved that over voltage has been controlled effectively with the chosen resistor. The THD value of the primary current also decreased from 74% to 24% with the mitigation. The main limitation of this mitigation technique, that is resistor, is it consumes 200 watt at 230 volt. This table shows the percentage change of transformer parameters without mitigation and with mitigation. Mitigation is being done with 130 ohm resistor. So, the comparison of methodology used, I have 358 volt jump voltage using Rudenberg method and experimentally, but simulation shows that there will be around 603 volt. The difference between this primary current like 4.06 ampere and 2.268 ampere is due to the exclusion of harmonic components in the Rudenberg method, whereas the deviation in the voltage and current with respect to simulation and Rudenberg method is due to the exclusion of initial flux and hysteresis effects in the Rudenberg method. Conclusion: this work is done by me for understanding what is jump phenomena with respect to a single phase transformer. With the help of Rudenberg method, the jump voltage and the inception voltage are predicted with the known capacitance value. A transformer is being modeled using Simulink to understand jump voltages under ferroresonance. With the Simulink model, a jump up of 2.6 per unit at the supply voltage of 150 volt has been identified, whereas it is only 1.55 per unit using Rudenberg graphical method. When the transformer is subjected experimentally without capacitor, the parameters of transformer has not experienced any jump up or jump down phenomena. But when a capacitor of 20 microfarad is connected to the transformer, all the parameters experienced a jump value about 1.5 per unit at the supply voltage of 150 volt and jump down at 60 volt. As per IEEE standards, the mitigation circuit is connected and it controls the ferroresonance effectively. Future scope: it is proven from the above work that jump resonance can be analyzed with the harmonic components during this fundamental mode, and hence both the periodic and aperiodic modes can also be analyzed with respect to harmonics. The design of harmonic based relay for all the periodic and aperiodic modes in the future may prevent damage to the instrument transformers. Thank you.